Okay, as I've said a while ago, the topic for today is finding roots of an equation, specifically the false position method. Now, in determining roots of equations, of course, you have your calculators with you that has a shift solve function. Now, if you are curious, what are the numerical methods that are used by calculators? Of course, it depends and it varies on the type of your calculator and of course and the method that you will use, how you will input the data. For example, we can use analytical methods in determining roots of equations. An example would be the quadratic formula. In the quadratic formula, we can readily determine the roots of a given quadratic equation. Now, for higher order equations, when you are now dealing with cubes to the fourth, to the fifth, etc. Now, the solution is not easy or not trivial. Then we resort to other methods. Now, as I've said, you can use your calculator. And we can also use other numerical methods, I should say. Now, one of the methods that falls under the bracketing method is the false position method. When we say bracketing, we are getting roots within the limits of or within 2 points, two distinct points, say point 1 and point 2. Now, the method of false position falls under this general category. Another category would be a single point approximation, that is using the one of the prominent example would be the Newton-Raphson method. In the Newton-Raphson method, you only need to specify a first guess or an initial guess for the root of the given equation. Now, in the method of false position, also known as regular falsi method, we are using a line to determine or to approximate, that's the correct term, to approximate the real root. Suppose that this is a given curve. The blue line represents the given curve. This is the given curve, and this is actually the real root, which is hard to determine. We can use the FPM or false position method to determine or approximate this root. Let's call the root, the approximated root as XR. XR lies along the line, this line. This line is formed when we join 2 points on the curve. The points on the curve are points 1 and point 2. Now, point 1 has coordinates, of course, x1, y1, and point 2 has coordinates x2 and y2. Take note that we are expressing y as a function of x. Now, regarding their coordinates, of course, we already know the points. Points P1 and P2, coordinates x1, y1, and x2, y2. We simply draw a straight line passing through these 2 points. Now, XR lies at the intersection of this line and the x-axis. Now, XR, or this point, this point of intersection has coordinates XR 0, 0 being the y coordinate. This is an approximation of the root. Now, the problem is how do we determine the value of XR? Now, the concept we shall use is Since this is a linear interpolation method, it uses lines. And of course, by using a similar triangles, we can actually determine XR. Now, from the figure, now the small triangle here, uh, this base, let's call this base and let's call this height. Base over height is equal to, using the concept of similar triangles, base of the larger triangle, base over height. Now, the negative sign affixed in here is to create a positive sign for the value of the denominator. Because naturally, since this point 1 occurs at the fourth quadrant, its y coordinate is negative. Then negative times negative, this is now positive. Again, this is using the concept of similar triangles. Base is to height is to base is to height. Of course, y2 is measured from this point up to that point, and y1 is measured from this point up to that point. And this distance is xr minus x1, and this base is measured as x2 minus xr. Now, solving for xr, we continue. Now, cross multiply, we have xr y2 minus x1 y2 is equal to x2 y1 minus xr y1. Solving for xr, transposing this term onto the left side and factoring out xr, we have this equation. Now, solving for xr, we can express xr in terms of this equation. Now, this is very cumbersome to use, not really easy to use. Let's try to improve on this one. Although this is already one of the forms of the FPM, false position method. Next, in order to manipulate the equation, let's add the term x sub 2 and subtract the same term x sub 2 from the right side. Now, we can simplify. Then we now have the final form of the equation for the method of false position. Again, xr is an approximation of the real root. Again, xr is an approximation of the real root. Now, in the illustrative problem, let's consider this equation. X to the fourth minus 5.1 x cubed plus 5x squared plus 5x minus 6 equals 0. Now, in this problem, we are to determine the real roots of the equation. And by the way, in the false position method, it is geared towards finding only the real roots. Now, there are cases where the method employed, the FPM, is not applicable. Now, let us also introduce the concept of percent error as applied in this situation. Percentage error is equal to the absolute value of the quantity expected value minus measured value divided by the expected value times 100%. Actually, the percent error is a measure of the divergence between the measured value from between the divergence between the measured value and the expected value. In a simple saying, we can say that the larger the percentage error, the larger the difference between the expected value and the measured value. In this case, we shall be using the term expected value for the real root, or the closest root that your calculator would provide, and the measured value, the value coming from this method, FPM. Now, if we examine closely the equation, we will
Sir,
notice
excuse
that
me
this
po.
is the,
Sir, pa-accept daw po yung iba.
okay. Let's try that. Again, for those that have just logged in, please write your name and the word, your name, your set, and the word login on the message box. Again, write your name and your set and the word login in the message box. Next is, again, our objective here is to determine the roots of this equation. The equation is now given. Again, you do not want to solve this blindly. You can use your shift solve calculator, but how do you know if the value you are getting is the only value or close enough value to the real roots? Therefore, we have alternatives just like this one. We have the FPM method. Now, using a spreadsheet software, we can easily plot this. Curve. Of course, the choice of x coordinates and y coordinates will be dependent on your skill as a user of the spreadsheet. However, there are I shall not delve deeply on this topic, plotting using a spreadsheet, because there are YouTube tutorials that you can readily access through the internet. Anyway, I think this involves around 2 or 3 steps in the most common spreadsheet programs available. Next, again, you can use Microsoft Excel for this one, for graphing this one. Now, of course, in here, I'll just show you a sample. In here, I have provided x values decreasing by increasing by positive 0.2 as you go downwards or downwards. For example, from 0 to 0.2 in here. Then y values would be using this x value to input in this formula. If you can see, this is entry cell A4. Using that, A4 to the fourth minus 5.184 cube plus 5A4 squared plus 5A4 minus 6. Of course, this should be small on your screen because this is already on the equation box. Then dragging this downward, then I'll just show you how do we arrive at this plot. I'll simply highlight these two, then right click, then I think insert, then chart. In here, you can already choose the chart. Use XY scatter. Then you can choose smooth lines only. Smooth lines. Then finish. Now you now have your plot. Delete this one, this entry. Then delete that one. And that is just one way to plot this one. Anyway, that's not the focus. I hope you can perform this on your own through exploration. Next is we continue with this topic proper. Now, after plotting the curve, let us focus on this root. Again, I've said that the number of roots depend upon the degree of this algebraic equation. This is an algebraic equation. Then it seems that there are 4 roots. Root number 1, let's call this root number 1, root number 2, root number 3, and root number 4. This is, by the way, this is the x-axis. The curve touches the x-axis at exactly 4 points. Now, let's just focus on this point. Let's call this root number 1 as our example in using the FPM. Let y be a function of x. Let's just copy the equation. Then replace 0 with y. Y now becomes f of x, or a function of x. Recall that the formula for XR is this one. Now, again, focus on root between 3 and 4. Now, our x1 is 3. x1 is 3. x2 is, in this case, our limits would be between 4 and 3. x2 is 4. The problem is, how do we determine y? Again, recall that y is a function of x. Just substitute x value in this equation, meaning that this would be to determine this one, y1 is equal to, simply equal to 3 cubed minus 5.1 times 3 cubed minus or plus 5 times 3 squared, then plus 5 times 3 plus or minus 6. I hope
Sir, hindi pa ba raised to 4 yung una?
you're talking about what was that? What was
Ay,
the
wala sir. Mali pala
interruption?
ako sir. Sorry sir.
What was the interruption about?
Wala sir, mali
Okay.
pala ako sir.
I think have your lunch already. Eat your lunch first, then okay. Thank you for that interaction. Next, this is again 3 to the 4th, then minus 5.1 times 3 cubed plus 3 squared times 5 plus 5 times 3 minus 6. This would be equal to negative 2.7. The same method can be used in determining y2. Just plug in, the term is plug in the value of x in this equation. Then there is a method in determining if the next iteration will be in between xr and x2, or in between xr and x1. Next is determine the value of xr. Again, xr is equal to this one. This is a formula. Plug in the values of x, x1, x2, y1 and y2 in this formula. Again, this should give us 3.103, which is a positive value. Remember, we are determining the root of this equation, and xr in the first iteration is an approximation of the root. First approximation, that is xr. In the same manner, yr can be determined using this formula. Plug in the value of 3.103 in this equation. Then multiply y1, the value of y1, to yr. If that is positive, they are both negative, the value becomes positive in this case. Then the root lies between x2 and xr. Meaning, if this is 3.1, the root is still farther to the right, or to the right of xr. Remember that xr is in between 3 and 4, and that is 3.1. However, our true root is somewhat greater than 3.1. Therefore, it is in between xr and and x2. x2 being 4. It is in between 3.103 and 4. With that knowledge, we will now use the value of xr, 3.103, as our x1, and retain the value of x2 as 4. In this case, x1 becomes 3.103 and y1 becomes negative 2.007, equal to the previous value. Previous value is this one. Again, let's go now into the second iteration. Now, recalculate xr using the formula given. Then it should give us 3.173. Then, recalculate also yr. Negative, this will give us a value, negative 1.34. Again, as an observation, we can say that this is getting closer to the real root. We have 3.103. Then increasing, we have 3.173. Now again, we apply the same principle, y1 times yr. This is still greater than 0. That is greater than 0. The root still lies between x2 and xr. Meaning we expect a larger value of the root, larger than 3.173. Third iteration. Now we have, again, use the previous value from the last iteration, second iteration. This becomes 3.173, and this retains the value of, we plug in the value of yr in y1, then retain x2 as being equal to 4 because of this condition. This condition is satisfied. Then plug in the formula. Then again, xr is 3.217. This is still this is larger than 3.173, our previous iteration, or our previous approximation of the root. Then this is a negative 0.086. Then continue with the fourth iteration. Now, when do we stop the operation? I think one of the conditions is you have to use a tolerance of the percent error is less than 0.1%. How do we know that one? We determine the percent error. The percent error is the absolute value of the expected value minus the measured value divided by expected value. In this case, we use or a calculator to determine the expected value. The expected value is for most Casio calculator users, you can use the solve function of your calculator. In the solve function of our calculator, the expected value is the root is 3.282. Now I've taken fourth, or I have done fourth, fifth, sixth, seventh, and eighth, and finally ninth iteration to determine the a percent error that is compliant with the tolerance. The tolerance is less than 0.1, and this now becomes I think 0.06. Now in the ninth iteration, we now have a value of 3.28. Now this is a 3.28 XR. This is the closest so far approximation of the root. Now still, if we apply the formula, still the root lies between x2 and x1. In summary, I've summarized the FPM on a spreadsheet. The first iteration, again, the values are x1, y1, x2, y2, xr, and yr. y1 times yr. They are all positive in this case. Then let's compute the percent error. The problem is how do you manually compute for the percent error? We can use again the formula is percent error equal to the absolute value of the let's just call this the expected value minus the measured value divided by the expected value, then multiply this by 100%. That is our equation. Get the absolute value of this expression. Because we are interested in the percent difference, the absolute value of that one. For example, for the first iteration, how do I write this one? How do you get this one? This is the percent error is equal to the expected value is 3.282 less the first approximation is XR is 3.103. Let's divide this to get the absolute value of that one, then divide this by the expected value 3.282, then multiply that by simply multiply this by 100. That would be the operations used. Now this should give us 5 point. The result should be similar to this one or close enough to 5.45. That is how you compute the percentage error. I think this is introduced in your chemistry classes or a physics class, depending on your case. The concept of percentage error, and also in I think in surveying one. If you have a surveying one, I think this concept is also introduced, the concept of percent error. Now again, iteration 1, percent error is 5.45. Then iteration 2, 3.32. Then down to the ninth iteration, which is 0.06. This is already now less than 0.1 tolerance. The tolerance is should be less than a point. The percent error is now less than 0.1. Now, I'm just interested if I continue with the process, how long should I till I arrive at the value 3.282? No, how many additional iterations will I perform in order to get to the root value was 3.282. That is, I think, 11 iterations. That is already 0.000 something. It's not anymore recorded. I'm using 2 digits after the decimal point. It's already 0.00 something. Now, in this presentation, it is just presented as 0.00. Okay. Now I'll be stop. I'll stop the recording